Imagine you are sitting in a high-stakes AI engineering coding interview. The clock is ticking. The prompt hits the screen. You are tasked with building a machine learning data pipeline, and you are staring at two distinct data sets.
Yeah, usually it's like a table of users and maybe a table of their transactions.
Exactly. And the base question they give you seems almost insultingly simple. Just show all users and their order amounts.
Right. Sounds easy enough on the surface.
But before we even talk about syntax, I want you to literally pause and think about how you will solve this interview coding question. How do you actually connect fragmented data under strict, time-bound interview conditions?
It's a completely different ballgame when someone is watching you type.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Glad to be here.
So, up until now, writing queries against a single isolated table probably feels, like second nature to you. But real-world ML pipelines just don't operate in a vacuum.
They absolutely don't. And honestly, that is the perfect scenario to test a candidate. I mean, if you are training a machine learning model, your data is inherently fragmented across distributed systems.
Right. It's like having unmixed ingredients in a kitchen. They are totally useless on their own, but powerful when you combine them correctly.
That's a great way to put it. The transition you have to make in an interview is moving from this mindset of isolated tables to understanding dynamic relational systems.
Because you can't build features for a model if you can't link the data together.
Exactly. So today we are going to examine the behavioral quirks of keys at scale, the critical algorithmic differences between inner and left joins, and most importantly, we are going to expose a deadly execution trap that ruins countless FANG-level interviews.
I love that we are tackling that trap because I've seen so many smart engineers fall for it. So let's get right into the architecture of the problem.
Let's do it.
Looking at the data set we are working with, we have two primary structures. Table 1 is our users table, contains a user underscore ID, a name, and a country.
Okay, pretty standard demographic data.
Yeah. We have 4 records. User 1 is Amit from India. User 2 is Sarah from the USA. User 3 is Raj from India, and User 4 is John from the UK. That is our base data set.
Perfect. And the second data set is the orders table. This one contains an order underscore ID, a user underscore ID, and an amount.
So this is our transaction log.
Right. And looking closely at the data, we have order 101 for user 1, Amit for an amount of 500. We also have order 102 for Amit for 300.
Okay, so Amit is a repeat customer.
Yep. Then there is order 103 for user 2, Sarah for 700. And finally, order 104, which is logged to a user 5 for an amount of 200.
Wait, hold on. I'm looking at the users table, and there is no user 5. We literally only have users 1 through 4.
Yeah. Keep that anomaly in the back of your mind. It is a very common real-world data integrity issue that interviewers use just to test your logic.
Oh, that's sneaky. Okay.
It is. Now, to solve the anchor problem of showing all users and their order amounts, we first have to identify the relational constraints. You already know what a primary key and a foreign key are.
Right, in the users table, the primary key is the user underscore ID.
Exactly. And in the orders table, the user underscore ID column acts as the foreign key. It is the bridge between the two sets of data.
But I'm guessing identifying the bridge is only the first step.
Oh, absolutely. The interview truly begins when you have to decide how the database engine should actually cross that bridge.
Well, the default reflex for most engineers is just to use an inner join. It's the standard matchmaker,
Right, it's the one everyone learns first.
So if we write this out, we are asking for users.name and orders.amount. The syntax would be from users inner join orders on users.user underscore ID equals orders.user underscore ID.
Yes. You are instructing the engine to evaluate the tables and find intersecting rows based strictly on that specific identity condition.
So let's look at what the execution engine actually does with that query.
Right. It evaluates the on-in condition strictly. User 1, Amit, satisfies the condition twice because he has 2 orders. So the engine generates 2 rows for Amit.
Makes sense. And user 2, Sarah, satisfies the condition once. So the engine generates 1 row for Sarah.
Exactly.
But wait, what about Raj and John? They are users 3 and 4, but they don't have any corresponding records in the orders table.
They don't?
And then we have that phantom order 104 for user 5 who doesn't even exist in the users table. If I'm reading the engine's logic correctly, the inner join just drops all of them, like they vanish from the output entirely.
They completely vanish. And that's because an inner join acts as a strict filter. If the on condition evaluates to false or unknown for a given record, that record is discarded from the result set.
Just thrown out.
Yeah, thrown right out. In an engineering interview, the moment you realize data is being dropped, a massive warning light should flash in your head. You have to ask yourself, do I care about the missing data?
Well, in the context of machine learning, I would argue we care deeply about the missing data.
Oh, absolutely.
Think about building like a churn prediction model or a customer lifetime value model. If we use an inner join to build our training data set, we are literally erasing every single user who hasn't made a purchase yet.
Right.
We end up feeding our model a data set where 100% of the users are active buyers.
And that is textbook survivorship bias. Your model will learn patterns based exclusively on successful transactions.
Which is terrible if you're trying to predict who won't buy.
Exactly. It will completely fail to recognize the behavioral patterns of users who register but never buy,
Yeah.
which is arguably the most important demographic for a business trying to grow.
Wow. So the database didn't fail, the math didn't fail, but your data engineering was fundamentally flawed.
Yep. Just because you used a strict intersection instead of preserving the driving table.
Which brings us to the left join. If the business requirement, or the interview prompt, dictates that we must maintain the integrity of our primary user base regardless of their transaction history, we have to swap the tool.
We do. We change it to from users left, join orders on users.user_ID equals orders.user_ID.
So what happens to the output now?
The output shifts dramatically here. The execution engine still gives us Amit twice and Sarah once, but the left join forces the engine to preserve every single row from the left table.
And just to clarify for everyone listening, does left literally just mean whichever table I typed first in my from clause?
Yes, exactly. The table declared first is the left table. So because users is on the left, Raj and John are injected back into our result set.
But the engine still has to output a value for the orders .amount column, right? And Raj and John didn't spend anything.
Right. They have no matching records.
So what does the database do? Does it just put a 0?
No, it populates those missing relational fields with NLL. And the generation of NLL values is a critical pattern.
Okay, why is it so critical?
The engine is basically saying, look, I preserved your user, but the requested data from the right table is fundamentally unknown. From an ML perspective, this hands the problem back to the data scientist.
Oh, I see. Now you have a feature engineering decision to make.
Exactly. Do you use an imputation strategy? Do you fill those NOL amounts with a 0? Do you use the mean order value across the platform?
Right, so a left join doesn't magically solve the missing data problem, but it surfaces it. So at least your model isn't trained on biased, invisible gaps.
That is exactly the point. It leaves no one behind from our driving data set.
Okay, that makes perfect sense. But this brings us to the part of this deep dive that is notoriously dangerous. The traps.
Ah, yes. The interview killers.
Because everything we've talked about so far assumes the engineer writes the syntax perfectly. Let's talk about what happens when the pressure is on, the clock is ticking, and someone forgets the on-end clause entirely. Like they just write select star from users, comma orders.
Oh, man. You've just created a Cartesian product. It's often called a cross-join.
And why is that so bad?
Because without an all-in clause, the execution engine has no logic to filter the relationships, so it defaults to matching every single row in the first table with every single row in the second table.
It's like a really bad speed dating event where everyone is forced to match with everyone else.
That's a hilarious way to picture it, but yeah.
The time complexity on that is just a nightmare. It's O of m times n. Amit matches with his own orders, sure, but the engine also matches him with Sarah's order and that phantom user 5's order.
Right, it just multiplies everything.
If I have 1 million users and 10 million transactions, I just instructed the database engine to generate 10 trillion rows in memory.
And you will immediately trigger an out-of-memory error and bring the entire production database to its knees. Interviewers look for this.
They want to see that you instinctively tie your join to an on condition before you even start thinking about the select statement.
Exactly. It should be muscle memory.
Okay, so omitting the on clause is a fatal error. But I want to get to the much more subtle and frankly much more common trap.
The left join plus where trap.
Yes. This is the deadly trap.
Mm-hmm.
I'm going to pose a logical scenario for you. Let's say I'm building a data set. I want to keep all of my users, so I know I need a left join. But I only want to look at high-value transactions. Let's say orders strictly greater than 500. As an engineer, my immediate instinct is to write my join and then just slap a where clause at the very end to filter the results.
Which is what Almost everyone does.
Right. Something like from users left, join orders on user underscore ID equals orders dot user underscore ID, where orders dot amount is greater than 500. Why wouldn't I just do that? The join happens, then the where clause filters the results. That is standard operating procedure.
It is the most intuitive, logical-sounding approach, and it means you just failed the interview.
Wait, really? It completely fails.
Completely. To understand why, we have to stop looking at the query as text and start looking at how the SQL execution engine actually processes operations in memory.
Yeah, I'm tracking.
It follows a strict logical order of operations, and select is actually almost at the very end.
All right, let's trace the engine's logic step by step then. Break down the execution order for that exact query.
Okay, phase one is the from clause. The engine identifies the users and orders tables. That's simple enough.
Yep, got the ingredients.
Phase two is evaluating the on-end condition. It looks for the intersecting records where user underscore ID matches.
Okay, so it finds the matches.
Then phase three is the outer join step. Because you specified a left join, the engine takes the users who failed the on-end condition, which are Raj and John, and adds them back into the virtual temporary table sitting in memory.
Right, and it pads their missing order amounts with NLL.
Exactly.
So at the end of phase three, we have our desired dataset. Amit is there, Sarah is there, and Raj and John are there with NLL amounts. We haven't lost anyone yet.
Yet. But then we hit phase four, which is the where clause. The engine takes that virtual table from phase three and evaluates your condition, orders dot amount greater than 500, row by row.
Okay, I think I see where this is going.
It looks at Amit's 500. Is 500 strictly greater than 500? No, so it discards the row. Amit's 300, discarded. Sarah's 700.
Kept, and then it evaluates Raj and John. But their amount is NLL.
Exactly. And how does a database evaluate NLLs greater than 500?
It evaluates to unknown. It's not true, it's not false, it's just unknown.
Yes. And where clauses discard anything that doesn't explicitly evaluate to true. So the engine strips Raj and John out of the table entirely.
Oh, wow. You just defeated the entire architectural purpose of the left join.
You really did. By placing a condition on the right-hand table in the where clause, you forced the engine to drop the NLL records. You accidentally converted your left join back into an inner join.
And you reintroduced the exact survivorship bias we were trying to avoid in the first place. That is a phenomenal breakdown. It's not a syntax error at all. It's a logical execution error.
Exactly. The code runs, it just gives you the wrong data.
So how do I fix it? If my business logic strictly requires keeping all users, but I only want to analyze orders over 500, where does that filter actually belong?
If your goal is to filter the rules of the match itself before the left join adds the missing records back in, you must move that condition into the on-end clause.
So I change it to left join orders. On users.user underscore ID equals orders.user underscore ID, and the orders dot amount greater than 500.
Yes. Let's run that through the execution engine just to be sure.
Okay, so phase one is the same. Tables are identified.
But in phase two, the on condition, the engine evaluates both the ID match and the amount at the same time.
So Amit's orders failed the greater than 500 test right there. Raj and John have no orders. Only Sarah's order passes phase two.
Right. But then phase three kicks in, the outer join step. The engine looks at the left table and says, Amit, Raj, and John didn't have any matching rows from phase two. I must add them back in with NLs.
And because there is no where clause waiting in phase four to ruin things, the final result set preserves every single user.
Exactly. Amit, Raj, and John all show up with NL order amounts, and Sarah shows up with her 700.
You successfully filtered the right table without sacrificing the left table. That distinction is literally the difference between a junior engineer and a senior data architect.
It really is. It fundamentally comes down to understanding the purpose of the operations. Where is a post-join filter? It filters rows after the connection is finalized.
While on is a pre-join filter, it dictates the matching logic during the connection phase.
When you're sitting in that interview, you need to verbalize that execution order. Don't just quietly write the code.
Right, talk them through your thought process.
Tell the interviewer, I am placing this condition in the on clause because placing it in the where clause would force an evaluation against NOL and inadvertently convert this into an inner join.
That shows such a deep mastery of the underlying database engine.
They will love it, I promise you.
Let's zoom out a bit. We've spent a lot of time dissecting the execution engine. For an engineer focusing on machine learning, how does this actually fit into the broader system architecture? Because we aren't just writing queries for the sake of querying.
We write these queries because data merging is the literal foundation of feature engineering. A machine learning model requires a unified, flattened matrix of features to train on.
So you have to pull from everywhere.
Yeah, you might have user demographic data in a PostgreSQL database, real-time transaction logs in a Kafka stream, and maybe historical product reviews sitting in an S3 bucket. You have to join them.
So if we build a holistic view of the SQL architecture required to build that unified matrix, it looks like a sequential pipeline.
It does.
We use join as the engine to physically connect the fragmented tables based on our relational keys. Then we use the on clause to dictate the rules of those connections.
Right.
And we use where to filter the individual rows after they are joined.
And then you move into aggregation. You use group by Y to roll that data up. For example, maybe aggregating thousands of individual transaction logs into a single total underscore lifetime underscore spend feature for each user.
That's a great feature for an ML model.
It is.
Yeah.
And finally, you use having to filter those aggregated groups, perhaps keeping only users whose total lifetime spend exceeds a certain threshold.
Okay, so let me summarize that mental model. Join connects.
Mm.
On defines the match. Where filters rows. Group by aggregates. Having filters the aggregates.
That sequence right there is the blueprint for almost every data manipulation problem you will face in a technical screen.
It's the blueprint for relational databases entirely. But I know there is one final concept we need to touch on that pushes the boundaries of traditional SQL and acts as a gateway into advanced AI architectures. Because we've talked exclusively about joining table A to table B, but the relational model actually allows a table to join with itself.
The self-join.
Yes, the self-join.
Yeah.
I've always found the concept a bit recursive, honestly. In what scenario would an ML engineer actually need to join a table to itself?
Think about the data structure behind a recommendation system or like a social network's friend suggestion algorithm.
Okay.
You don't have separate tables for users and friends of users. That would be wildly inefficient. You just have one massive users table and a mapping of connections between those same users.
Oh, I see.
So to figure out who your friends are, the engine has to take the users table and join it to an identical instance of the users table in memory.
Right. You are establishing a relationship within the exact same entity class.
Yeah.
That is fascinating. And honestly, it's a great transition to our wrap-up.
It's a deep rabbit hole to go down, for sure.
So today, we took those isolated, unmixed ingredients and learned how to build a unified data set. We explored the strict intersection of the inner join and how it can introduce serious survivorship bias into ML models.
A huge pitfall.
We then leveraged the left join to preserve our primary data sets, and we walked step by step through the database execution engine to understand exactly why a where clause on a left join is a fatal interview trap.
The key takeaway from all of this is to always visualize the data flow. Understand the difference between filtering during the match with on and filtering after the match with where.
If you can articulate that difference clearly, you will absolutely stand out in any technical interview.
No doubt about it.
As we sign off, I want to leave you with a provocative thought based on that self-join concept we just talked about. We mentioned using it to map out friend connections. But what if your ML model needs to find friends of friends of friends? To traverse that network, you have to keep joining that exact same table to itself over and over, compounding the complexity.
It gets messy very quickly.
At what depth does a traditional SQL relational engine simply break down under the computational weight of its own nested relationships? And how does that specific mathematical bottleneck force modern AI engineers to abandon SQL entirely in favor of graph databases?
That is the million-dollar architecture question right there.
Something for you to mull over as you prep for your next architecture round. Keep exploring the execution engine, and we'll see you on the next deep dive.